Hi everyone, I'm Guillaume and I'm going to talk about tracking memory leaks in GStreamer or your GStreamer application. So my name is Guillaume, like I said. I work for Collabora and we have a bunch of nice stickers over there and goodies, so help yourself on the table. So we all hate memory leak. Why? The first obvious reason is because it increases memory consumption. So if you run your application on a very small device or embedded device, that may be a problem. You don't want to waste any memory in your laptop either. If the process is running for a very long time, it may be killed by the kernel at some point because it eats too much memory. And that might also lead to weird crash. For example, if objects which are not supposed to still be there but are staying around, they may try to use devices which are not ready to use anymore, or things like that. So that's really something we want to prevent at all costs. For that, we have a bunch of tools which have been around for a while. I'm going to present them first, then why I developed in the last month. The obvious choice when you want to detect leak is Valgrind, which is very, very common. I guess a lot of Linux developers are using it. It's very powerful. It will detect all different kinds of leaks. So if you allocate a string, which is not free, for example, after, that's something it will detect. It will give you a full stack trace, which is very useful because you can see all the code will lead to the memory being leaked. And we have GST validate support, which actually is something I implemented a while ago. So you can run all the GST validate test suite using Valgrind, which is pretty cool to catch these kind of things. So it's nice. But it may lead to some problem. First of all, it's a very low-level tool, like I said. So sometimes you don't really care about every single piece of memory, but you want more like a big overview, like which GStreamer element are being leaked, for example. It will give you that, but it can be a bit tricky to find what you really care about in all the output. And the second very big problem, it's very, very slow and CPU consuming. That means if you want to run a very complex case, it might take literally hours, which is not very convenient if you want to do that. For example, each time someone submits a patch, you want the QA system to automatically catch that up and try to run all the tests with it. If it takes like 1 day to run all the tests, that's not something you can do automatically, which is a bit annoying. Also, if you are doing embedded development, you may not have Valgrind, which is built for your platforms. So sometimes it's not always convenient to use. And, hello. Yeah, it's a very right system. So if you want to use that in a QA system to automatically reject patch leading to leaked, but if the leak is in another component which is not related at all to the GStreamer code you modified, you may have a lot of false positive. We have a way to suppress that, which is the Valgrind suppression file. But they are very dependent of the type of system you are running. So for example, if you are updating the libc library, you may have new leaks because they won't be catched by the suppression file. So that's pretty annoying. Another tool we have, which is GStreamer specific, is the GST ref counting debug category. So if you turn that on, in your GStreamer log, you'll see all the allocation of object, all the destruction of object, when an object is ref, when an object is unref. It may be useful, but for automatic debugging, it's not really what it's made for. So it may be useful to help you, but not to... Thanks, Louis. One other tool we used to exist until the new GStreamer version is Gst-trace. It used to be an internal debugging tool, but it was used to track a GST object and GST mini object, which is something very useful because usually when you are writing GStreamer code, that's what you really care about. But the problem is it had a lot of false positives as well, because some objects are intentionally leaked in GStreamer. So it's not really a leak, but it's just statically allocated, and it's not supposed to be destroyed for various reasons. But those were detected by the system. So it was not a really good candidate for automatic QA tools, because if you can remove those false positives, it's impossible to detect real leak from false one. So first, I wanted to use this tool, and I tried to find a way to detect this false positive. So yeah, that's the kind of things Gst-trace will give you. So this is working with all GStreamer version except the 1.10, which is coming because it's been removed. I'll explain why. But it will give you all the objects which are still alive and their address. That's basically it, which is already pretty useful. So I'm going now to talk about the system I implemented. So like I said, first I wanted to have a way to detect the false positive reported by Gst-trace. And I introduced two new flags on the GST object and GST mini object class, which we decided to call maybe leaked, because it's going to be, yeah, everyone, okay. So if you have my Twitter, you want your photo, know it's a good time. We call it maybe leaked because, okay, this object is maybe going to be leaked at the end of the process. So if it's still alive, okay, that's fine. It's not, don't see that like a real leak. So that means that now a developer, when they write code, can just set this flag on the object, on the mini object, and we won't care about it using the automatic leak detection tool. So then I started to use that, so this flag with the existing Gst-trace program. But I've been told by Sebastian, I think, saying, okay, this is cool, but maybe you could use the Gst-tracer infrastructure, which is a new technology which was recently introduced in GStreamer, which allows us to, yeah, okay, hello Olivier. This is going to be to replace existing debugging tools. So if you are going to write something new, maybe you should use that. So what Gst-tracer does basically, it's loaded at runtime, and it allows you to get information about what's going on in your GStreamer pipeline using a bunch of hooks. And you can send formatted output about what's going on, so external application may eventually read that and use that to do various stuff. So like I wanted to learn about this thing, I decided to use it as well. And I had to introduce two new hooks, which are the created and destroyed hooks. I introduced them on the object class and the mini object class. So if you are not familiar about the distinction, every big object in GStreamer is a GST object, and all the small ones which are created and destroyed very regularly are mini objects like caps, like event, and these kind of things. But yeah, at the end of the day, you are always interested about which objects are leaked, so I had to introduce it in both. And I introduced a new Gst-tracer, which I call Gst-leaks, which is going to track all the creation of the object and media object, all the destroy, when they are destroyed as well. And when your project, your application is being terminated, it will list all the objects which are still alive, so which have been leaked because they have not been destroyed at the end of the application, and raise a JLeap warning, which is very useful if you are running a QA tool. You can just store this one as fatal, and that will be detected by your QA program. So it's a bit tricky to use at the moment because you have to say, okay, I want to load the leaks tracer, I want to have the tracer debugging as well, so you can see actually what's being leaked. We are thinking about an easier way to do that, so hopefully it will be easier soon. And then you just launch your GStreamer application. So it can be a GST launch pipeline or whatever app you are using. Or you can just type make check, and it will run all the test suite with that. And you'll end up with this kind of output. So at the end of the execution, it will say, okay, this object is still alive, you have the address, you have the type name, so that can help you debugging things. The ref count, so if the ref count is really big, that means a lot of references are still around. If it's one, you just have to find this one. And that's it. So that's a very useful information. You can start to try debugging things. And I also introduce filtering support. So that means if you know that you are tracking, for example, a caps leak or text pool leak or whatever, you can say, okay, I only care about this kind of object, and that will reduce the overall memory footprint of the tracer because it won't have to log and keep in memory all the objects allocated. So this approach has a bunch of advantages. The first one is definitely it's much, much faster than Valgrind. A colleague of mine said, oh, your tool is great, it's like Valgrind, but actually fast. So it's much more convenient to use. It's going to be integrated in GStreamer itself. So in the upcoming 1.10 release, you'll have it available by default, which is really cool because you don't have to worry about building external tool like Valgrind, for example, to debug. It's very QA friendly because it's fast and it will raise a glib error if it detects any leak. And this may be seen like an advantage or disadvantage depending on what you care about, but it will just detect code in GST object and GST mini object. So all the leaks in other libraries you are using won't be detected, which may be a bad thing because at the end of the day, you really want to have all the leaks being detected. But if you just want to decode your very own code, which is usually the first step, that's much better because you don't have to look in all the stack trace you're not really responsible of. So that's cool. And now we have a way to detect, well, to indicate when an object is supposed to be leaked. So if all the false positives have been marked, they won't be listed as leaks anymore, which is very cool for the QA tool as well. So this worked actually pretty well. I spent a lot of time debugging all the unit tests in core, base, good, bad, and ugly. And I fixed a lot of leaks, some in test, some in the code itself. So it proved itself to be useful. Then once I have that merged, I had a couple of extra features which I found useful. The first one is the lib unwind support, which allows us to get the full stack trace of the object being linked. So for example, here we have a caps which is being linked, and we see we have here a trace property with all the call which lead to the leak. So the top one is when the object is being initialized, and here you can see it's somewhere related to template caps. So that really helps you to see what's going on, and you are pretty much the same information that Valgrind will have to give you, which is always useful. Another thing I had is the signal support. So here by signal, I mean Unix signal. So this part is Linux specific, but all the rest, so everything I saw, including the stack trace, it should work on all the platform. I didn't test it because I'm just using Linux, but I think it should work on Windows, on Android, on macOS. If you try to use it and it doesn't work, please open bugs because it's supposed to be multi-platform. But yeah, this point is not because we are using Unix signal. So it's a feature actually I implemented age ago in a small project called GObjectList, which is a GObject debugger to debug memory leaks, and I re-implement it here inside my my tracer. So to be able to use it, you first have to define this environment variable. The reason is by default we don't want to catch Unix signal because your application may already be interested into a signal. So be careful before turning that on to make sure the two signals here are not already used. And what the handler of this signal will do is pretty simple. when it catches the seek user1 signal, it's going to log all the alive objects. So that means you can have your application running, like a GUI application, like a video player or something. You send this signal using the kill command on the command line, and you'll have in your debugging output all the objects which are currently still alive. So that may help you to see what's going on in your application. If things are too slow, if things are not working properly, you can check, okay, this object is still alive, it should not be alive at this point, or, okay, I have way too many objects, or some objects are missing, so that may be useful. And the other signal is to use what I call checkpoints. So a checkpoint is just, you create a checkpoint by sending this signal, and the second time you send this signal again, you will see the delta between all the objects which have been created and destroyed. So it may be useful if you want to see what's going on between two specific actions in your application. So for example, if you have a web browser, you can just start playing a video, create a checkpoint, then stop the video and close the web page or something, and then you can see, okay, which object has been created, which object has been destroyed, which are still alive, and that may help you to see what actually happened during the execution of this action. So it's a bit niche, but sometimes that's the kind of things which can be useful. So now I'm going to talk briefly about few tricks you can use when you want to debug leaks, because like I said, I spent a lot of time making sure that all the tests in GStreamer were leak-free. So I'm going to share with you a bit of experience again while doing that. So if you want to use my tool in your application, the first thing you have to do is make sure that gst-dinit is called before returning. So at the end of your main function, you want just before returning, you want to call that, because that's this call which will destroy the leak tracer and start detecting which object are still alive. So it's very easy, you just have to add this call if it's not there yet. Then hopefully you won't have any leak because your code is perfect, right? But if it's not, that may happen, you will have all the output, the debugging output, which contain all the leaks which have been detected. And why I suggest generally is try to focus on the top leak, because if you see that there are dozens of caps which are leaked, you see there are paths which are leaks, that may mean that actually it's an element which is being leaked, and if the element is not destroyed, all the objects it's managing are going to be destroyed as well. So there is not much point trying to debug every single caps if fixing the element leak will magically fix them all. So try to focus on the bigger object. Remember that this will only means GST and GST money object. So if there are other objects which are being leaked at all, but which are not subclass of those, they won't be detected. So keep that in mind as well. And another trick I suggest is if you are really using this feature, so that's the command, the environment variable you have to enable. So you'll have the stack trace here. It may be useful to do some filtering. So the filtering is what I show here, because that means each time an object is being allocated, I'm going to save all the stack trace in the memory. So if we do that for all the objects, it's going to consume a lot of memory. So if you are debugging a caps leak and you want more information, first filter. So the memory footprint will stay not too high, hopefully. Another trick I use a lot is using GDB. So GDB is the GNU debugger, as you probably know, and it can do a lot of useful things. And one of those is you can ask him each time a specific function is called with a specific argument, please do something. And I'm using that and to catch each time an object is being ref or unref. So you do that by, you say, okay, I want a breakpoint on this function, but only if the object, which is the argument of the function, is this specific address. You can do that with the unref as well. And then you say, okay, each time I enter these two breakpoints, I want a stack trace, and then you continue. And by doing that, it will generate you a lot of debug outputs, but you'll be able to see where is your object being refed and where is your object being unrefed, which can be very useful to see, okay, if at some point a component is taking a ref, but it's never getting it back, so unref is never called, well, that means that there is probably a leak over there. That's very useful, but the problem is it can be very, very long because a lot of objects are being refed and unrefed all the time. So what I suggest is each time you see something about a GObject signal or a property, so where property are set, JLib internally take a lot of ref and then unref them. Usually you can just ignore that, and that will make the logs you have to go through much, much smaller. And something which I discover is often the source of a lot of problem and a lot of leak is what we call ref counting transfer. So in glib and GStreamer especially, we had a lot of transfer full API. So that means that the function which is being called is responsible of unrefing or taking ownership of the object. And if it doesn't, then you'll have a leak. So usually I suggest to start looking at those in your code path. They may be one of the culprit. And a few GStreamer API can be very tricky to debug when you're tracking ref counting. And one of those is the probe code. So we have the GST paid probe handled return code, which is exactly the same as another one. But the difference is this one is supposed to unref the object and the other one are not. So it can be very easy for a developer to just forget about it or to change the return code, but don't think about changing the ownership management of the object. So that kind of things can be tricky. So yeah, that's usually the place I would suggest you to start looking if you have very tricky leak that you can find, because I found a lot of those bugs with those. And that's pretty much it. Which further improvement could we have for this tool? First, Thibaut wrote a patch to improve the stack trace. So to have the file, the source file, where the code is being called, and the line of the source code. So we'll have exactly the same kind of trace that Valgrind give you, which is very useful. Hopefully it should be merged soon. And then I don't know, maybe we could use that to have a graphical user interface tracking the objects which are alive and see that, but using, I don't know, some kind of nice graph or something. It's a bit tricky to know exactly how we want to display that. Maybe that's something we could do in the GST Debugging GTK tool, I don't know, just a thought. And if you have suggestions as well, so if you are using the tool and you think about how it could make your life easier, don't hesitate to talk to us or just file a bug. And that's all I have. Do we have questions? Mm-hmm.
Where's the documentation?
That's a good question. Inside the GStreamer core, so the leak tool itself is in the core, so in the GStreamer repository, there is a documentation about all the tracer, so not just this one, but the tracer, and there is some doc there. So if you look in this text file, you'll see all the environment variable I mentioned, which are documented, and you'll have example and everything, so you can just start from there. So in the core Git repository, you'll find that. Good question. Yes?
What is the criteria that you use to filter out all the false positives?
So the question is, which criteria do I use to filter out the positive? So I don't use any myself, the false positive, yeah. So I don't use any heuristic at all. So it's the responsibility of the developer, which is introducing an object which is going to be leaked, to use this flag. So they use they set the flag on the object, and the tool will know that it's actually supposed to be leaked. So it's the responsibility of the guy writing the code to use that. But yeah, this flag have been merged in GStreamer 1.10 as well, so you can use it directly in your application. It's public API now, so you can use it directly. And
does it work for legacy code as well?
yeah, of course. Well, Well, no. You need to have this flag, so you'll need at least 110. Yeah, you'll have to port your application to GStreamer 110, and then you can start setting these flags on all the objects which are expected to be leaked, and then you can use the. But you'll need the new GStreamer anyway to have the tracer. So yeah. Anything else? Yes. Okay, so the question is what the performance overhead of the tracer, and I have to say that I didn't do any strict measuring, so the official answer is I don't know. In practice, on my laptop, which is a decent machine, it doesn't seem to have a huge impact. It probably increased a bit the memory, but in practice, I didn't notice. The whole test suite doesn't seem much slower to be run that without the tracer. It probably is, but for my day-to-day use, it's not something I noticed. I didn't test it on embedded device, so I suspect if you have a very much smaller system, it may have an overhead, but I didn't have the chance to do actual metrics, so I don't really know. Huh? Okay, so the question is, how far away are we to automatically destroy all the leaked objects and so have some kind of garbage collection? That's what you mean? Yeah, well, I think in theory it should be doable. In practice, I will not recommend that because we are writing C code and it's not really in the spirit of the language to do automatic garbage collection. And if you do that, I suspect you'll create more problems that you solve. So I think the right approach is really to do a lot of tests, detect all the leaks and then fix them properly. Then you'll have better code than trying to fix your very badly written code using other hacks. It's not something I would suggest. But yeah. Okay, it was the last question apparently, so thank you very much.